Welcome back to another LeetCode video. We're looking at the problem of the day, LeetCode 2300, successful pairs of spells and potions. It's a medium problem, and yeah, we should just get into it, and I'm going to show you how to solve it. So we're given two positive integer arrays, spells and potions, of length n and m respectively, where spells at position I represents the strength of the ith spell, and potion at position j represents the strength of the jth potion. You're also given an integer success. A spell and potion pair is considered successful if the product of their strengths is at least success. Now we are supposed to return an integer array pairs of length n, where pairs at the ith position is the number of potions that will form a successful pair with the ith spell. Right, and there's some constraints here where we are guaranteed to have at least one potion and one spell. And also the spells and potion values are always going to be positive, as well as the success number. Right, so how do we approach this? Well, looking at the constraints, since the arrays might be the same length, how could we approach it? Well, actually, let's just put this into the drawing board and have a look at these examples real quick. So what do we have? Well, we have the spells array here, we have the potions array here, and we have an output of 4 here. And the way that is computed is that we multiply the first spell, the 5, we multiply that with every value in the potions array, and then we get this result. So we see now that 5 times 1 is 5, times 2 is 10, etc., etc. And since our success value is 7, we only count those values that are larger than 7. Now here, the potions array is sorted, the spells array is not sorted. And if we go down to this example here, we can see that the potions array is not sorted anymore. And we also see that the results are also not sorted because of that. So the correct approach for us will be to try to sort the potions so that then we only need to find the position from which on all multiplication with spell will yield a successful pair. Otherwise we would have to, we'd pretty much have to iterate through all of these multiplications, which is going to be O of n times n time, right? If we go through all of the spells, and each spell gets multiplied with each portion, that is O of m times n time. And we want to bring this down to something where we have n, and then if we just find how many potions are correct, then we'll have a log n complexity. So we'll bring down the runtime to m log n with that. So, but what do we need to do for this? Well, we need to sort the potions array once. By the way, we could also approach it the other way, right? That we sort the spells first, and that for every potion, we look at how many spells have, how many spells actually work. But then we would have to keep track of what are these spells, and we would have to put them into a sort of a sorted array where we put the position as well. So we'd have we would have 1 would be at the first position, but also at index position 1. So we would carry the index with the number, then we would have value 3 at index 2, and we would have the value 5 at index 0. And if we want to figure out if a potion is successful together with a spell, well, we would do binary search on this array, on these values. And then we would have to extract the index, and in our result we would have to add +1 to whatever the index is that we stored. So at index 2, in this case, we would add a +1 where this 3 is right now. Yes, so this is a little bit more convoluted. So we're going to try it the other way, where we just sort the portions and then we do the binary search, not on the portions and not on the spells. So, but I just wanted to mention that there are two approaches to that. So we'll have some time and some space complexity. Now, first thing we'll do is, well, we'll sort the potions. And the second thing that we need, well, we need some result. And we know that we should return pairs, so we're just going to name the variable pairs. And in the end, we're going to return them. Now, what we will do is for each spell in spells, we're going to count how many successful portions we'll have, right? And count, and we have to call a helper function here. And then we just do append count. And well, what should our helper method do? Well, it should count the successful portions, right? For potions and for a given spell. That's what it should do. And so let's add this here, potion spell. Right. So now we only need to flesh out the helper methods now. And well, how do we do this? How do we do this? Well, with binary search. So we're going to do the usual left, right equals 0, length of spells -1. You should really know this pattern, how to do binary search. It should be, you should be able to do this in your sleep. Right. And in the end, we're just going to return a count, right? So we need to initialize a count variable. And now we need to do the binary search, and for that we need to compute the element between left and right. There are different ways of how you can calculate this. I find this the easiest way, right? What you could also do something where you say left plus the difference between right and left plus 1/2 or something like that. But I like this better. It's the simplest way to do this. Just add them both and do an integer division. Right, so now the big question, well, what is our condition going to be that we will use to decide to go into the left or the right sub-array of potions? Well, if potions at position mid, well, we need to multiply it with the spell, right? And then compare it to success. So if that times the spell that we pass into the function, if that is larger or equal to the success required for a potion spell combination to be successful, well, that means we found a correct count. And it also means that we're going to continue to explore in the right sub-array. Sorry, in the left sub-array. Because we might get more. With count, we're not counting how many elements are to the right of mid. But it doesn't mean that maybe there's another position mid that is smaller than the current one, where we will still have successful combinations of spells and potions. So, and I'll flesh out the count in a second. So just the other case is just where we go is mid +1, and this is mid -1. Right, so, well, how do we count how many elements are to the right of mid? Well, it's the length of the potions minus mid, right? Easy enough. So that is everything we really need. And well, okay, we need to write down, what the runtime complexity is. So let's just think about this. So in terms of space, well, we need the pairs, and the length of the pairs array depends on how many spells we have. So if we say n is length of potions, and we say m is length of spells, then we know we need O of m space. The sorting is done in place, so we don't need any extra space for that. And our binary search doesn't really store anything except the count and, of course, left and right pointers. But that is a constant amount of space and will not change over overall space complexity. Now, in terms of time, well, we have to perform our log on, well, our search on the potions array, which has length n. So we'll have a component of log n. And then how many times are we going to do this? Well, spell times, right? So that would be then m times log n. That's pretty much all we need to do. Now let's see if that works. Okay, we have a typo somewhere. Spells. Yes, because spells, we have spells the array and we have spell the parameter that we pass to the function. Let's try again. Okay, both tests were accepted. And now for the big test, we're going to submit this. And we're getting the wrong answer. So why would that be? Let me see. Let me see. So we're getting spells 39, 9, and we're getting potions. And potions equals this. So let's just go through our logic. Successful potions. So we're sorting the potions. That is right. The expected is 0. Expected is this. Sorry, 6. But we're getting 0, 6. Is something maybe off with our math? Well, if we sort these numbers, that would be 22, 22. What else do we have? 29. Then comes 35, 37, 40. 40, right. So in the first case, how many successful pairs? Oh, and then we iterate over the spells. And the success is 320, right? It's 320. So what do we get when we multiply? Do we need to do some math here? Potions mid times spell is larger or equal than success, right? We're doing the right branching. So I'm just checking now if we're doing the right thing in our binary search. But I don't see anything wrong with this. All right. So what we will do is we will check, well, we'll print the potions here as well when they're sorted. And we would expect this to be this value. And now when we do the binary search count, we initialize it with 0 in the beginning. Well, left is smaller equal. This also seems, all of that seems correct, to be honest. And maybe we should print this. So combination. That is this, and success combination at the index at mid is this, and required is that. Let's see what happens. Okay, combination at 0 is that, at 1 is this. Oh, I'm such an idiot. Look at this. We are iterating over the length of, well, just the length of spells. Well, we are searching within the range of spells, not within the range of potions. Well, obviously that can't work. So let's remove the debugging output again. And yeah, that is because in the test cases, Well, the second test case, we had the same number. And in the first test case, the boundary was always within the first 3 items, which is why the error was invisible when we ran the test cases before. You know, the test pass again, and now let's submit again. All right, so there you are. So this is a little bit more efficient than the brute force method, where we just actually compute all the combinations of potions and spells in m times, that would be m times n time. And well, we brought that down to m log n time. And this concludes this daily problem.